Thank you, Pierre. Thanks for the invitation. It's a great pleasure to be back home, say, to this room and give the talk here in the analysis seminar. So I'm going to speak about a joint work with Alessio Figali, Xavier Rosoton, and Joachim Serra. They are all in Zurich. And it's a joint work that we finished at the end of July, and you can find the paper in archive. And we solved a problem that I ran after for 20 years, more or less. So we are quite happy. So let me explain you the story. Well, this is just simply the simplest semilinear elliptic equation, minus Laplace u equals f of u, and consider solutions in a bounded domain, say, var n. N is the dimension. As you all know, the equation comes from an energy. So there is a Dirichlet energy, potential energy. Capital F is the primitive of small f. And if you make the first variation, you get the equation. Then we will look also at the second variation, right? The second variation is the linearization of the equation. So you get an operator which is minus Laplace minus a zero-order term, f prime of u. And we will say that the second variation is non-negative, definite, if this is a positive or a non-negative operator with Dirichlet boundary conditions. And this turns out to be the same as the quadratic form, associated quadratic form being non-negative. It just means this inequality. You have this inequality for every test function psi with compact support. And then we will say that the solution u of the equation is stable if the second variation of energy is non-negative definite. And therefore you have this extra information to the equation. Look that in the equation there is this, the nonlinearity is f. Instead here what appears is f prime, right? So I didn't specify a boundary value, so this definition applies to any boundary value. But this definition corresponds to these competitors. You add to u a perturbation that has compact support, so you are not changing the boundary values. So the game among competitors is always competing with guys that have the same boundary values as myself and you. Our interest, bad nonlinearities, bad in the sense for regularity or for a priori estimates. Bad means that f is going to be non-negative and it's going to be large at infinity, so even more than linear, superlinear at infinity. Very simple observation: if f is superlinear at infinity, there are no absolute minimizers of the energy. Take any function, scale it with a large parameter, look at the energy. This is quadratic, of course, and this is super quadratic. If t goes to plus infinity, this goes to minus infinity. So the energy is not bounded below. There are no absolute minimizers. So now the natural question: are there stable solutions? And the answer is yes. There are plenty of examples, interesting examples, where there are non-trivial stable solutions. This already appeared in 1963. It was proposed by Gelfand at this equation with the exponential. These are the model nonlinearities that I'm going to take, but let's focus, say, on the exponential, for instance, where you add a parameter in front. You see, you add lambda times the exponential, and the parameter lambda is going to be important. This is a model in combustion theory. That was the motivation for Gelfand. So these we call Gelfand type problems, and a key assumption is that f of 0 should be strictly positive, like in this case, or like in this power case, 1 plus u to the power p. f of 0 being strictly positive makes that 0 is not a solution anymore. 0 is not a solution. In fact, it's a sub-solution. Lambda will be positive. It's a sub-solution. So the energy, in fact, if I draw looking like you like this, the energy a little, at 0, it starts with negative slope because 0 is a sub-solution. At infinity, it's going to decrease to minus infinity. If lambda is not too large, you can check that the energy should make something like this. So it should have a local minimum, at least in one, if you make the drawing in one direction, a local minimum, a mountain pass, say, a local maximum in one dimension, and then go to minus infinity. And this is what happens. You can prove that if f of 0 is positive, is non-decreasing, convex, and superlinear at plus infinity, so bad nonlinearity, say, for a priori estimates, then no matter what the domain is, in every domain you can prove very simple, quite simple to prove, and this was done long time ago, that there exists an extremal parameter, lambda star, which is positive and finite, and for every lambda between 0 and lambda star, there is a stable solution which is positive, so non-trivial, and it's stable. It should be there on that minimum, say. It is classical, so for these ones, you know that they are regular solutions. As lambda converges to the extremal parameter, what you get is a weak solution, say a distributional solution, which is still stable because the stability condition, you see, passes through the limit beautifully by monotone convergence. Everything is monotone, increasing. And this we call it the extremal solution of the problem. And in general, all what you know is that it's L1 and it's distributional solution. And then you can prove that there are no solutions for lambda bigger than lambda star. And this is a general setting in every domain, but an important first paper was due to Joseph and Landgren some years after, where they do the radial case, also with the exponential and the powers, but let's focus on the exponential. In the radial case, they use ODE techniques, and they can see they saw that there was a qualitative difference, important difference, depending on the dimension. Up to dimension 9, this in the unit ball, right? Up to dimension 9, this is the branch of stable solutions. It's increasing. You can get this branch through the implicit function theorem, in fact, all the way to lambda star. You can get it by the implicit function theorem. And what they saw is that the limiting solution, extremal solution, was bounded. I'm plugging here the L infinity norm. And then these are mountain passes, Morse index 1. When you turn again, Morse index 2, Morse index 3, Morse index 4, and infinitely many turning points about a parameter here that I will tell you in a second which parameter is this. Instead, in dimension 10 and higher, the branch blows up. As lambda goes to lambda star, blows up in the sense the L infinity norm of the stable solutions blows up, and the weak solution U star is unbounded. Bounded and bounded. In fact, the singular solution is explicit, is just the logarithm. It's a quite mild singularity at the origin. It's very simple to compute the Laplace of this guy and see that it solves for this equation. 2 times n minus 2. Lambda equals 2 times n minus 2. Now, you look at then you ask yourself, is it stable or not stable? You look at the linearized operator, minus Laplace, minus 2n minus 2, exponential of this guy is 1 over x squared. And this is a beautiful operator because these scale the same. They scale the same. Therefore, you have Hardy inequality, and Hardy's inequality tells you the solution will be stable even only if this constant is less or equal than the Hardy constant, which is n minus 2 squared over 4. I'm always in dimension 3 or higher. And this means n greater or equal than 10. So for this you don't need ODEs approach, say, and this already shows that in dimension 10 and higher there are explicit stable singular solutions. And since these are the only stable solutions, there cannot be two stable solutions for the same parameter. In these dimensions, the extremal solution, which is stable, is this guy. Instead, in lower dimensions, this guy, which is always a weak solution, is up here. It's up here on this turning curve like this, and this parameter is exactly 2n minus 2. And the guy has infinite Morse index, so lots of negative eigenvalues, because you overpassed Hardy's constant. All right. So after this picture, well, for the powers, you also have explicit solutions. It's always nice to have, they help you. And these are powers. For power blow up gives you power nonlinearity. Just from computing the Laplacian. So now the question is, the question that arises already in the 70s, as you will see, is when the extremal solution, or more generally stable solutions, are bounded, or when can they be they could be singular, right? That's the question. And does the dimension play a role or not? So these are the questions. When is the extremal solution, or in general stable solutions, bounded or not? Let's just make a short parenthesis. You know that for general solutions, so if I don't consider stable solutions, but just general solutions, to prove an a priori L infinity a priori bound, this requires, maybe except some very special cases, but in general, I would say 99.5% of the examples we know, for general solutions, you are able to prove an L infinity estimate if and only if the nonlinearity is subcritical or critical, right? And for supercritical nonlinearities, there are singular solutions, like the logarithm, for instance, or the powers, when you are supercritical, okay? When you are supercritical. So that's the answer, say, a general answer for general solutions. But now we are interested in stable solutions. So the first result, before, note that if you know maybe a little about minimal surfaces, all this thing of dimension 9 or 10, and an explicit guy reminds you a little of the story of minimal surfaces and minimal cones. For minimal surfaces or minimal cones, there is also an explicit guy, very easy to write, which is the Simon's cone, which has zero mean curvature. Then one computes, makes the analog of this. One computes when is the Simon's cone stable or not, and it appears that the Simon's cone is a stable minimal surface in dimension 8 and higher. And the results of minimal surfaces, well, if you focus on stable minimal surfaces, pretty much everything is still open. When are stable minimal hypersurfaces in Rn regular? It's not true in dimension 8 and higher because there are examples. It's true in dimension 3, and this is already 40 years result, 40 years ago result by Fisher, Colbury, and Sean, and independently by the Carmo and Penn. So in physical space it's true, but still open in dimension 4 to 7. And many people would kill for solving this, right?
Sorry.
Let me just say one thing. If you add that minimal surface is not only stable, but it's a minimizer of area, then the problem is known up to the sharp dimension 7, right? And these are the works of Simons, Georgi and other people, Almgren.
So stable here means that the second variation is non-negative.
Exactly.
But there might be zero direction. The difference between stable and minimizer.
Here also there could be zero. No. The difference between stable and minimizer, I mean, well, what depends what you. When you speak about minimal surfaces, when you speak about minimizer, you mean an absolute minimizer.
Global minimum.
Global minimizer. All right? Yes. So stable is very close, I agree with you, to being a local minimizer, say. But we accept zero eigenvalue, so it could be degenerate, all right? It could be degenerate. And also here. So this is a very important open problem in minimal surface theory. Back to our analog, say PD analog. The first result, besides the radial case studied by Joseph and Landgren, the first result is from 75 due to Crandall and Rabinovitz, and they were able to prove the L infinity bound for stable solutions up to the good dimension 9 if the nonlinearity looked very much at infinity, very close to the exponential or to a power. And this is a strong condition that they have that involves f prime, f double prime, and forces the nonlinearity. The condition forces the nonlinearity either to be very close to an exponential or to a power, and no other possibility. So it's a condition about the limit of f times f double prime over f prime squared. And depending on the value of this limit, you fall here or you fall here, nothing else. So I can still ask you, what if I put exponential of u? This argument does not apply. This is due to that in the equation you have f, and in the stability you have f prime. So different things. Sorry? The lambda plays no role. You can put it in front. Yeah. The lambda plays no role in the sense that there plays no role in these L infinity estimates. Okay. If you find an L infinity estimate, it will be an infinity estimate for all stable solutions for all this branch. So, but in any way, this branch is increasing. So you see, the lambda plays no role.
So these were, I mean, Lundgren and
Joseph
were radial, just doing ODE.
This was just radial, but this is the good thing. This is in every domain. Thanks for pointing out. This is our interest is in general domains. Of course, the radial case, in principle, should be easier. But Joseph and Landgren do the radial case, but they do phase plane analysis. They also need to know how the nonlinearity behaves. So they just focus on the exponential and the powers. So then it is mainly Chaim Rezis who insisted in this problem when after my PhD I started a postdoc in Paris. So these are the year 96, and he was working on this problem and the associated parabolic problem, and they proved nice things for the parabolic, some for the elliptic also, and he started insisting in this question. Well, first, a nice question also, is the extremal solution in the energy space, depending on the dimension, depending on the domain, and that was open back to that time. And then even more important, what about the L infinity estimate? So Rezis in a paper wrote, is there something sacred about dimension 10? Is it possible to construct, he writes, is it possible to construct a singular stable solution in low dimensions for some domain and some f? So at that time we still didn't know. I'll tell you when I started to believe that the result had to be true. But at that time we were not sure. Because he had a student, Grégoire Nedev, that worked in this plan for his thesis, which is a very hard problem, in fact, to work in the thesis. But he quit math after, maybe he got In fact, I know that Brezis feels a little bad about it, but he got a very nice result. He got, and this is not easy. This was not easy. He found the L infinity estimate for stable solutions up to dimension 3. And he included almost all nonlinearities. Well, he just needed the usual conditions that we call Gelfand conditions or Brezis conditions, f of 0 positive, non-decreasing, convex, superlinear. So everything is increasing. Just with these conditions, he proved that stable solutions are bounded in dimension 2 and 3 in every domain. And he got the energy that the solution is H1 up to dimension 5, and in every dimension if the domain is convex. I'll tell you about the proofs later. I started working on the problem back then, but my first result was in 2005 with my student Antonio Capella, where we did the radial case. And in the radial case, finally, we were able to prove the L infinity bound for every f, no condition at all. And the bounds are, as you will see later, the bounds are independent of f, but this will come later. This is the moment when I thought that the result probably was going to be true, because in the radial case, you can embrace all the nonlinearities, right? Then I kept working on it, and 5 years later, I have a paper I really like. It's in CPAM that solved the problem up to dimension 4. And I with no condition on f again, so very general result for any f, and it was mainly an interior estimate. We will come to the estimates in a second, how they look. I needed convex domain if you want the boundary regularity. I'll tell you about proofs later. Then Salvador Villegas in Granada was able very nicely combine my proof and Nedev's proof and remove the convexity of the domain and push the energy result, the solution is in H1 up to dimension 6. And then we kept working, involved many other people, for instance my student Xavier Rosoton. We did a nice thing like the double revolution, functions that depend on one radial variable and another radial variable, and then we were able to go up to dimension 7. Then I involved also Joel Sprague, who got interested in the problem. We got a result up to dimension 5, but with conditions on the nonlinearity, so we were not so happy. This is now the results with Alessio, Xavier, and Joaquim. This is the interior estimate, which is quite amazing, as you will see, because everything is very universal and it looks linear. You take it's an a priori estimate, so take a regular solution of a semilinear equation, and the only assumption we need to make is that f is non-negative. This still we need to assume. Not in my CPAM paper in dimension 4, only up to dimension 4, any f. Here we will need f non-negative. So u is superharmonic and u is a stable solution. Then we prove in every dimension what we call a higher integrability estimate for the gradient. The gradient, we can bound it not only in L2, but a little more, L2 plus epsilon, 2 plus gamma. In the interior, by the weakest norm you can put here, the L1 norm, and with a universal constant, depends only on the dimension. It's like a linear estimate, right? I'll tell you a little about this.
So there exists gamma such that, or for every gamma?
No, there exists gamma that depends, here it says, this is the way I mean it. There exists a gamma that depends only on the dimension n, and for every f, and for every u. This is an interior estimate, big 1, big 1/2, and looks linear. How is that possible that looks linear? Gamma is here, 2 plus gamma, a little more than H1.
Yeah, so H1 is from speed of stability and energy estimate. This is little bit improvement of
the H1 estimate is not easy to find for stable solutions, and up to this moment it was only known up to dimension 6.
Oh,
Yeah. Villegas, here.
so this is super harmonic, right? Super harmonic. So, and you have inequality. Now, FU is locally, or F prime is also F prime is
And then up to dimension 9, this is the big open problem. Up to dimension 9 included, there is even an L infinity or a holder, even a holder bound, which is beautiful, universal, independent of anything. Okay? So how is this possible that they look like linear when this is a nonlinear problem? Well, for a linear problem, the energies, well, I mean, this is not an explanation, and maybe I shouldn't say this here at Quran, but let me say, if the problem is linear, the energy is quadratic, right? It's quadratic. So for a linear problem, the energy is quadratic, and bounds are linear, say. Here we are in the energy is not quadratic, of course, but we are around a solution which is stable, and being stable means that at least in a neighborhood, suppose that it's a local minimizer, at least in a neighborhood the energy should look like quadratic. And when we will use the stability estimate, the stability assumption, all what we will be doing are small perturbations, because it comes from doing small perturbations, the stability. So this is saying, when I use the stability estimate, I'm just looking around the solution, and there things are quadratic, say the energy should look quadratic. So this is the only explanation I can say to say to students. So allow me for it. But this is how they look, right? With the this interior estimate, this is also an interior estimate. Then if your domain is convex, you can combine this with moving planes. And you can prove from this an immediate corollary. If the domain is convex, up to dimension 9, you have an L infinity global estimate for stable solutions of these problems. Now for first time I put zero Dirichlet.
That's convexity in one direction of ice?
Convexity in one direction.
You need convexity altogether.
I think I need it all together, but I should think a little more about this. But I think I need it all together. Because it could be like this. Okay, I have to think about it. Luis, good question. Never thought about it. Then you ask yourself, well, what about global regularity in general domains, if the domain is not convex? Or a version of this on the boundary. This is our second theorem, and it says, okay, it's more difficult to prove this. It's not, sometimes boundary regularity is easier because the boundary data helps you. Here you will see in the proofs it's not so much the case, and we need more assumptions on the nonlinearity. We need F to be non-negative, non-decreasing, and convex. F should be convex. And then you take a stable solution of the Dirichlet problem. It's going to be a positive solution because it's super harmonic. Then you have the global higher integrability and the global holder estimate up to dimension 9. And still the exponents are universal, they just depend on the dimension. So these are the two main theorems, and then, well, corollaries. The corollary is that the extremal solution is always in the energy space in every dimension, and it is bounded up to dimension 9, no matter what F is. And then also say that in dimension 10 and higher, our proof gives sharp estimates also, but are weaker than L infinity, of course, and what we get is sharp Morrey type estimates. The solution is in LP, and the gradient is also in another LQ, and with a rate of growth for the a rate of growth for the LP norms involves. So these Murray norms. Okay, so those are the results. We can start now with proofs, okay?
I have a question.
Yeah,
So again, stable means like we have to think about it as
stable means this.
proper minimizing, right?
Think about it like this.
But in general, how can you?
No, it means that the linearized operator minus Laplace minus f prime of u with Dirichlet boundary conditions has all the eigenvalues. It has infinite eigenvalues, a sequence of eigenvalues. They are all non-negative.
So in general, any solution you can put an index to it. Like
Exactly.
That's the
Exactly.
But then can you extend things?
We
like-
don't know if this can be extended to Morse index 1 or something like this. This work for people. Maybe yes, but it has been done for some nonlinearities. For some nonlinearities, some things that we know for stable have been done, like power nonlinearities, have been extended to Morse index, finite Morse index. But for any f, I'm not sure. I'm not sure. Good question.
So there are no counter examples even in higher Morse index.
There are no counterexamples. Good question, Nader. There are no counterexamples. At least, no. In the radial case, when you write something which is singular, at least the examples we have, once it is not stable, all examples we have, when it's not stable, it just overpass this Hardy constant and it has infinite Morse index. Good point. So this is the stability condition, and let me tell you that it will be very important in the proof. Well, up to here there is no information, but it will be important to make a good choice for a function that we will call it C. We will call it C. So I'm going to choose psi to be C times eta. Eta will be less important, say. Eta will be arbitrary. But I will have to make an important choice for C. When you plug this psi equals times the product of two functions in the stability, just integration by parts, this transforms to this, becomes this. The gradient square, but now with this weight, C square. And here you see the linearized operator computed on C. So it will be important to make a good choice of C so that this helps you in a way, or this gives you information. This I did for first time in the radial case, and I was, as some of you may know, I was motivated by minimal surfaces, or the Simon's lemma on minimal cones. On minimal cones, it's very important to make this choice, still have freedom for eta, but to choose the right C. And in minimal cones, the right C is the second fundamental form of the cone. So the curvatures, all the curvatures squared of the cone. And then in the semilinear case, it becomes this. Good. I wrote it there on top. So let me tell you about the proofs. In the paper of Crandall, Rabinovich, and Nedev, this C did not appear. In fact, their choice of test function psi is semilinear. Say they choose psi, a function of u, h of u, for h to be determined depending on the nonlinearity f. And the first time when this C appears is in my paper with Antonio Capella in the radial case. This was a natural function to try, RUR, because this will satisfy something for the linearized operator, because it comes from dilations. RUR is what you get when you dilate the domain. It's the same as X grad U. And this is what we chose with Antonio. And then eta, like in minimal cones, a power, always a power for the eta. And this brings, in the radial case, to dimension 9, to the result. Instead, in dimension, in the general domains, I change to another function, c, which is the modulus of the gradient of u in my paper up to dimension 4. And then eta is less important. So let me tell you, in the paper with Alessio, Joaquim, and Xavier, we need to use both this and this. Now you should ask me, so what is the linearized operator? The important thing is, what do these functions satisfy for the linearized operator? This is a trivial computation. Well, both are trivial, but this looks very simple, just dilations. And this is just a computation. It's the full Hessian square minus one column, the column that goes in the normal direction. The important thing is that this has geometric information. Within here, you have all the curvatures, principal curvatures of the level sets of the solution U. So this controls, because this you are going to put here, you see? You're going to put here. And this is positive. So this will give you a lot of information, and in fact it is a geometric information because you have curvatures of level sets and even more, and even more. And the idea in my paper up to dimension 10 was to combine this geometric information coming from stability together with a Sobolev inequality on general hypersurfaces, the level sets, that is called the Michael-Simon and Allard inequality. It's a geometric Sobolev inequality, universal geometric Sobolev inequality, where curvature plays a role, and that was the key point in this result. Now let me show you the key lemma in the paper with in the current paper. The key lemma is this: we go back to the other test function x grad u, and you plug it. You know the linearized operator. You plug it in the stability estimate, and the left-hand side becomes this. Here looks bad because there are second derivatives, but you all know that this can be integrated by parts, like in the Pogozaev trick, in the Pogozaev identity. You can integrate it by part and get rid of second derivatives and just get first derivatives. You do this and you get this lemma, which is the key point. For every dimension, for every nonlinearity, for every stable solution, for every test function, you have three terms, and the whole thing is non-negative. The first term, or term 0, involves grad u square. Instead, the second one involves what I will call from now on, to speak faster, ur square. Ur is the radial derivative of u. And here there will be also ur and probably ur. So these ones go together, ur square. Their sign is not so clear a priori. Instead, this is grad u square. Grad u square is stronger than ur square. So you better make 0 positive, right? Or 0. If not, if this turns to be negative, you are done. You can throw this. You need to make this non-negative. So now eta is going to be a power, a negative power. The biggest I can make it. The most negative I can make it, the best. But this term 0 is telling me, be careful. This should be non-negative. The best you can do is to get this exponent, 2 minus n over 2. And then it makes this exactly 0. I still need to take a cutoff near the boundary. But
You're not assuming convexity.
no, I'm just doing the interior estimate, say. I'm in a ball big 1, and I will get something in big 1/2. But the test function must vanish on the boundary. So this theta here will be a stupid function just dying between big 1/2 and big 1, okay? But the power, you see, is important because it's blowing up at the origin. Later the origin will be any point, huh? It will be any point, but I'm fixing it to be the origin. So this guy, you choose this so that this is 0, in fact. When the test function falls in this, you will get error terms. But now the important guys are 1 and 2. And now you compute 1, you have to make the gradient of eta square, this square, 2 minus n. So there will be a 2 times n minus 2. 2 times n minus 2. And then you have to make gradient of eta square. So this guy, square, n minus 2 square over 4. Remember that this was the constant in the Gelfand problem, and this was the Hardy constant? You make the algebra here, you make the algebra, and you get n minus 2, 10 minus n. So this is the magic of the whole thing. And this I found in 2014 to tell you the story of the whole thing. So five years ago, say. What you get is something that will be useful in dimension 3 to 9. Dimension 10 and higher, you get nothing from this computation. I will have to change the power. But up to dimension 9, this is perfect, and you get something which is good, but not too good. In the sense, look, this is a beautiful non-dimensional quantity. First derivative square, so minus 2. The 2 kills the minus 2, and minus n kills the Lebesgue measure, so this is adimensional. This means that I'm very close to L infinity, an L infinity, or some norm which is adimensional. You don't know so many adimensional norms, right? The L infinity, but you know another one also. The John Nirenberg, the BMO. the BMO. But before talking about that, what do you get? These two terms combine and give you this, but then remember, gradients also fall on this test function, theta. But this test function lives in an annulus, because the test function theta is 1 here. So just on the annulus, this is very important. Ball annulus. But here the bad news is that you get the same weight, but you get the full gradient square instead of UR square. So we have this. If you do this at any point, it's very easy. Just using Poincaré inequality and the John Nirenberg lemma say, well, it's very easy to prove, well, it depends on the, well, I mean, from the definition, you just use Poincaré inequality and you get that the solution is BMO. And by John Nirenberg is in LP for every P. So this we had 5 years ago. Up to dimension 9, the solution is in LP for every P. It's even BMO for every nonlinearity. Yeah, I don't need even F non-negative, any nonlinearity. Stable solutions are BMO. And then I talked to some people, renowned people. I talked to some, I explained this to some people, right? But we didn't succeed. We didn't succeed. With the Zurich team, it took 2 visits. So it took first 3 years ago, like a intensive week with Alessio. Xavier and Joaquim were my PhD students. They knew this when I did it 5 years ago. They were finishing the thesis. And then, so that was 3 years ago in Zurich, 2.5. And then last November, we were in Zurich. I was in Zurich again. And I was kind of stubborn. And I said to the 3 of them, come all together to my office and let's have a last try. And then we found it, and I'll tell you very fast the idea. Well, this I can do very fast. You all know the whole filling technique. If we had that in the annulus I can bound the whole gradient square by the radial derivative square, then we are finished. Because then you would have the same thing on the left and on the side and on the right. Here an annulus, you do the whole filling, and you get a constant less than 1 here. So when you get inside half the ball, you gain, things decrease. Things decrease in an algebraic way, and you get Holder continuity, and you are done. So this was the point. Can we have this or not? And for general solutions, this is impossible. In fact. So on the other hand, I told them, well, on the other hand, there is a possibility, because if you are, suppose of the extreme case, if you are is 0, I think it's in the next transparency. So may it be true or not? Now I rescale everything. You see, this is a dimensional. My class of stable solution is invariant under dilation on everything, because I'm including all f's and everything. So I can just, to answer this, I can go like in the linear theory, I can rescale everything and go to the unit ball. Could this be true or not? Then I think we made really a real progress when I think I said, well, in the extreme case, it's not possible. I mean, suppose that this is 0 and this is 1. In the extreme case, suppose that this is 0, then U is 0 homogeneous. It's a 0 homogeneous, so it's a function that depends only on the angles. And it's superharmonic. So it's a function on the sphere. It is it has a maximum and a minimum on the sphere, but then it is a maximum and a minimum everywhere, because the function is 0 homogeneous. A superharmonic function cannot have a minimum. Contradiction. So U is constant, and then it's contradiction with this. But here, as you see, I didn't use stability. And what I know is that this estimate is not true in a quantitative way, is not true for general solutions. I knew the enemies. We know that this cannot be true. So stability, what we knew back then is this information that gives some hope, but does not use stability. And on the other hand, we knew that this, for general solutions, could not be true. So we had to use stability again. But you don't see it here, but this gives some hope. And at this point we said, okay, let's try to prove it by compactness. And if you use it, prove it by compactness, it's quite simple proof. You take a sequence and blah blah, sequence of nonlinearities, doesn't matter. You prove it by compactness, you can see that the problem will be to pass to the limit here. You will have weak convergence, but the grad U square could go to 0, right? Could go to 0. And you have to, and then you get no contradiction. So you have to try to preserve this. But now you see, you will get compactness using the higher integrability. If the gradient is not only in L2, but L2 plus something, for sure you will have a strong convergence in H1. Right? This is well known. So the higher integrability. How do we prove the higher integrability? It's using the other test function. Here in this whole story, we use this test function. To get the higher integrability, we use this other test function here. And we don't need the Michael-Simon, but we do it by hand. We do it by hand, and we get the W1 2 plus epsilon or 2 plus gamma estimate. So this is the proof. And then let me say one word very fast about boundary regularity. Well, boundary regularity, you cover your domain, and then you are in a situation like this, almost half balls. Almost half balls. Let's do first the simplest case, half balls. There are good news and bad news. The good news is that this function is good also in the sense that it vanishes on the flat boundary. Because now the solution U vanishes here, and it's whatever there. If you want to think of positive there. but vanishes here. So x grad u also vanishes here. The gradient points there, x points like this. So this is good on the flat boundary, and it brings you to this, the same thing. Same thing about annulus, but now half annulus, half annulus. And now these are the bad news. You ask yourself, is there a superharmonic function in a half space, say, which is not constant, and it's zero homogeneous? And the bad news is that yes, they exist. Just the angle. Just the angle. The sinus of the angle. I mean, just the sinus of the angle. So x2 over r, right? So this complicates a lot the boundary regularity, and we need a much stronger theorem. And here is when we need to assume the extra assumptions that f is non-decreasing and non-convex. And it's a very strong result. We were surprised in the beginning that we could even prove this, but everything is fine. It's a very strong compactness result, in the sense these are very bad nonlinearities, right? This could be exponential of exponential of exponential of u. And it says if you have a family of stable solutions, no matter what nonlinearities in this class, that they converge in L1 to a function, then this function is also a stable solution of some equation f, for some f. And some f which is non-decreasing, convex, and maybe blows up in finite time. Because the limit of increasing convex functions, there is always a limit of increasing convex functions, nonlinearities, they always have a limit. And it will be a convex nonlinearity, and increasing, but maybe it blows up before. And the solution u then will have L infinity norm less than m. This is incorrect. No, we assume it. Maybe we assume, yeah, maybe we assume that u is already continuous. Yeah, why not? Yeah. The important thing is that it's also a stable solution of a new equation. And then what we see is that this guy will not be a stable solution. Things like this are not stable solutions of a semilinear equation. This guy is super harmonic, but it's why? I can tell you why. Yes, here. Because then we use this, and the contradiction comes from the fact that if u were zero homogeneous, then it cannot be a solution of that. Because f of u is still zero homogeneous, and the Laplace of u is -2 homogeneous. And that's a contradiction. So this is the boundary irregularity, and this is my last transparency. Thanks for the attention.
The last theorem has no limitation, and it's still less than what
What was the question?
Here, the question of Fanhua is if the dimension, if there is an assumption on the dimension here or not. I believe that not the way it is stated, I should check, but then if you want to say,
we have C0 probably require 9 dimensions.
if you want to say that this convergence is in C0, then we need dimension up to dimension 9, for sure.
So just a little bit of thought that you have a previous page with inequality.
The basic lemma?
Yeah, basic lemma. You have
Yes.
this inequality. When you got this inequality, you can move the right side x to the power 2 minus x outside. Just divide us by rho to the power 2 minus, rho 2 n minus 2. You see what I mean? It's a homogeneity. But left side will tell you if you restrict to a smaller ball, this last line.
Oh, here, you're looking here?
Yeah,
Okay.
Right side, you just move x to the power 2 minus n outside the inequality. But the left side, you can say when
Yeah, these I can take out for sure.
When load
Here.
is small, that means Then it's done.
Ah.
Because the full gradient is bounded by just by choosing different.
I thought
and
about.
then your whole feeling, and then
I thought that will not work.
I know
This will not work. I tried to do this for 4 years, okay, until I realized that there is a counterexample. What Fanhua is saying is that pretty much what he's saying is that you have this information,
Yeah.
it's just radial derivative, but you have the freedom of the point y, the freedom of the point y. So now average in some sense with respect to y. I could bring you like this pile of computations. In the radial case, you are well. In the radial case, you are done. So what are the enemies for this? The enemies are. I can show you that this. I can show you that this does not imply L infinity
No.
for solutions.
Yeah. But you have a normalized quantitative case. You see
The enemies. Let me just say 1 second. The enemies are not right. What would be the enemies for this?
they're homogeneous degree 0 ones, sort of.
Homogeneous of degree
Like
0.
logarithm ones, yeah. Right? But I thought if you move this, we should talk about it.
Okay. You want to keep something on the right? Or?
No, the right hand side you can move over. Left hand side, when you move over, you can add any small constant and with respect to different. So respect to the normalized form, after you move over, the things will behave exactly. So I saw that when you iterate, then you work even more.
Okay, that would be nice. Let's talk about. Let me just add a word in this direction that now we can prove this lemma. We can prove this lemma in a quantitative way without the compactness. we can prove this lemma without the compactness proof. But initially I thought, okay, let's put it in the. But Alessio was very reluctant, and in fact he's right. He was right, like very often he's right, because this compactness proof is very flexible. And now I can do it for the P Laplacian. I can do it for for other problems. Very flexible. Instead, the proof that we have for this now quantitative requires it's not easy. And requires to have the Laplacian, and I don't know if that can be extended. But I'll be glad to hear Fanhua.
Can you make one comment there? It is connected to minimum surfaces.
Yes.
The second test function clearly related to that.
The second test function mod grad u is related to minimal surfaces.
So, for example, I know non-existence of a stable minimum, or say area minimizing surfaces or stable ones. Then can you see that directly? That why these solutions will be bounded? So you have to normalize it somewhere. Yeah. So that means the web minimum surface there, like a level set or something. Level set is compacted close.
Yes.
That's the new curvature surface after you follow up.
Here with this you get an information
About
not about every level set, huh?
yeah.
But just an integration
Yeah.
on all level set through the
It's
quad.
an analog, but not exact.
An analog of
Analog of Simon's state, but not exact.
yes. Yes, well, no. What in my paper in dimension 4, what I did is to take the Simon's
Yeah.
an analog of the Simon's lemma. You mean
Yeah.
that would say like what, like some kind of regularity or in low dimensions, or
Yeah.
like what?
Well, you have second fundamental S.
Yes. Would you like to even say that
No,
every
no,
level
I
set
don't ask that. I
every
just,
level set is regular?
No. I was just saying because you mentioned this dimension related to stable
Yeah.
minimum surfaces
Yeah.
and so on. But I see this here related to level set curvature.
Yes.
In some way I did the same.
Yes.
But I still don't see how
No, no, no. Yeah, sure, sure. I'm not using any result of minimal surfaces,
Okay.
and
There are some construction of these equations related to
oh yes, yes. Counterexamples are related to minimal surfaces for Allen Kant, for instance. Sure, for Allen Kant, but here I'm not using any result from minimal surfaces, and the analogy is not so strong.
Or the analogy isn't so great because
No.
they're, I mean, up to scaling, Alan Kahn becomes
Minimal surfaces.
base minimal surface.
Yes, not here.
So here there's no V-scale picture that
No.
you're working on.
No. These analogies are just are just some more analytical, I mean, tricks that prove that what things that you do, right?